Okay. All right, guys. Higgy here again for potential energy. Specifically gravitational potential energy. Now, I want you to get your head focused for just a minute on this word potential. All right, which implies that it's probably not moving yet. And there's all kinds of potential energy. If I take this calculator and I'm holding it so far off the ground, it has the potential to fall. All right, so we have gravitation pulling it down, gravity pulling it down. So that's gravitational potential energy. There's the potential for gravity to pull it down. All right, if I have a rubber band and I pull it and I stretch it out, then I have elastic potential energy. When I let go, obviously the rubber band will fly, but if I stretched it, elastic potential energy. A cookie, like you eat, has chemical potential energy in it. And because it's not making anything move yet, I haven't eaten the cookie to make my muscles move. So it has chemical potential. So there's all kinds of potential energy, but today we're going to focus on gravitational potential energy. And they all have their own little formulas that are related to whatever device the potential energy is found in. But gravitational potential energy, EP, most of the time you see it, or you'll see it EPG, whatever, is equal to the mass of an object times gravity, acceleration due to gravity, times how high it is, multiplied by how high it is. So we need a mass, and we know that the gravitational acceleration is always 9.8 meters per second squared. So we can kind of commit that to memory, and then all we got to do is know how high it is and multiply those together. So we have a pretty simple formula. It's a pretty simple situation. So let's look at our rock that's sitting, our 50 kilogram rock that is sitting on a 100-meter cliff. How much gravitational potential energy does it have? Well, come on, how hard is this going to be? Let me make my little writing a little smaller so we can put that up here. EP equals the mass, which is 50 kilograms, times 9.8. I just did that. Now we're going to do the gravity, 9.8 meters per second squared, times the height, which is 100 meters. I do all that math, and let me just get my little calculator here. So you have 50 times 9.8 times 100. And I come out with 49,000. Yeah, 49,000. And if you if you remember what we talked about yesterday, that energy is measured in joules, and we know that's 49,000 joules. And I'm not going to go into the units today. I'm going to do that a little bit later, but just know that it's 49,000 joules is the amount of gravitational potential energy that the rock has at the top because it's sitting at 100 meters. All right? So what I want to show you, though, real quick is that what can happen. All right? In our little real-life example, this rock could fall. It can start falling, and when it reaches 50 meters, it still has some potential energy even though it's falling. It has some kinetic energy too. We'll talk about that next week, but it has some potential energy. It still has some potential energy, but it doesn't have all of the potential energy that it started with at 100. It only has what it has at 50. So I can do the math again at 50 meters and calculate the potential energy at 50 meters. And when I do that, I find out that the mass is still 50, and I'm only going to write the numbers in this time. The gravity is 9.8, and the height now is 50. So I plug that into my calculator, and I'll find out what the gravitational potential energy is at 50 meters, and it's going to be 24,500 joules of energy that it still has halfway down. And I can calculate it anywhere in this path. I can calculate the gravitational potential energy at any point along the way as long as I know what the height is there. So like right here would be 25 meters, or maybe here it's 37 meters, whatever. I could calculate the potential energy that it still has because it will always be changing as long as it's falling, so that when it gets to the bottom down here at 0 meters, obviously if I were to plug in a 0 here, everything here multiplied by 0 would give me 0 joules of energy, of gravitational potential energy. All right? It's a pretty simple concept, pretty simple formula. You have a worksheet, I'm sure, Coach, I'll give you here in a little bit. Just make sure you continue to write the units down, because I'm going to show you something about units that are special with energy next week. You're awesome.